Good evening. Am I audible?
Good evening, sir. You are audible, sir.
Any doubt from last class?
No, sir.
Next, we have to plot graph related to these three different quantity, that is displacement, velocity, and acceleration. Next is graph of variation. First is displacement versus time. Second is velocity versus time. And third is acceleration versus time. For displacement, equation is y is equals to a times sine omega t. So curve related to displacement will be sine curve, which will be like this. Sine curve. Next is for velocity, which is omega times a cos omega t. So it will be cosine curve. Velocity versus time. And then next is acceleration, which is minus of omega square a sine omega t. That is minus sign dependent. So graph will be like this. So we have to define first phase relation between these two different quantity. To define phase, just proceed this curve slightly backward. So if you proceed this velocity to have starting at this point, and for acceleration, it will be like this. So from this part, we can say if initial projection for all these three different quantity is same. So velocity is ahead of displacement by pi by 2. And in case of acceleration, it is pi with respect to displacement. So we can say phase difference between displacement and velocity is pi by 2, and between velocity and acceleration is pi by 2, and between displacement and acceleration pi. So from this graph, we may define phase difference between these two different quantities. Next, we can say At mean position, displacement is 0, but velocity is maximum and acceleration is 0. This is mean position. Extreme position, this point, acceleration is maximum, velocity is 0, and displacement is also maximum. So we may define at different position which of the quantity will be maximum and which of the quantity will be minimum related to this particular graph. Abhinav, any doubt?
No, sir.
Okay, just draw this particular curve. Atif, done? Abhinav, done?
Yes, sir.
Okay, so this is all about the displacement, velocity, and acceleration related to SHM. Next is energy. Energy in SHM. As displacement is equals to A times sine omega t and velocity equals to omega times A cos omega t. In terms of displacement, this will be equals to omega root under A squared minus Y squared. So we have to define energy. A particle in SHM will have two different types of energy. One is potential energy and the other is kinetic energy. So first is potential energy denoted by U, which is equals to half k y squared, just like for spring mass system we did in chapter 6, work, energy and power, where k is called spring constant, which is equals to m times omega squared. I will derive this particular relation in next part of this chapter. K is spring or force constant. So you may write this expression as half. In place of k, it will be m omega squared y squared. Now, at mean position, when y is minimum, so potential energy will be 0. At extreme position, when y is maximum, so potential energy will be maximum, that is half m omega squared and a squared. Riba, any doubt?
No, sir.
Next is we have to define potential energy in terms of time-dependent equation. So again, we can say potential energy equals to half m omega squared y squared. So in place of y, we may write its general equation a times sine omega t. So it will become half m omega squared. In place of y, put a times sine omega t. So it will be like this. Now we have to transform this particular sine square theta into linear power. So we may write sine square theta equals to 1 minus cos 2 theta divided by 2. So using this, it will be 1 by 4 m omega squared a squared times 1 minus cos 2 theta, that is cos 2 omega t. Now from this part, we may conclude for displacement, we have angular velocity omega, which may define you its frequency of vibration or its time period. But in terms of potential energy, it is twice omega. So we can say potential energy vibrates with twice angular velocity, twice frequency, and having half time period as compared to that of displacement in SHM. Abhinav, is it clear?
Yes, sir.
Okay, just write it down to this part. I will summarize these relationships in last part. Okay. Rishan, any doubt? Yusuf, done?
1 minute, sir. Done, sir.
Similarly, we have to define kinetic energy of particle during this SHM. So next is kinetic energy of particle during this SHM. So K is equals to half mv square. So if you put the value of V in displacement dependent term, so it will be half m. V is equals to omega times root under a square minus y square. So it will give you omega square a square minus y square. Now we have to define its maximum and minimum value. So first, at mean position when y is 0. So if you put y in 0 in this equation, you will get kinetic energy maximum, that is half m omega square a square. Similarly, at extreme position, y is a. So if you put y equals to a in the part, you will get kinetic energy minimum, that is 0. So if you relate these two terms from the above part with respect to potential energy, you will say at mean position potential energy is minimum, but at mean position kinetic energy is maximum. Similarly, at extreme position potential energy is maximum, but kinetic energy is minimum. So these two quantities must be related with one another like this. Next, we have to define this quantity in time-dependent term as well. So we can write kinetic energy equals to half m v squared. In place of v, we may write time-dependent term as half m v is equals to omega times a cos omega t. Now, to transform this particular relation in linear power, we may write cos square theta equals to 1 plus cos 2 theta divided by 2. So using this relation, it will become 1 by 4 m omega square a square bracket 1 plus cos 2 omega t. Now again, from this part, we can say kinetic energy will oscillate with twice angular velocity as compared to its displacement velocity, or it will have twice frequency and half time period as that of normal equation. Riba, is it clear? Now we have both kinetic energy and potential energy. So on combining these two quantities together, you'll get total energy. So next is total energy equals to potential energy plus kinetic energy. Potential energy is half m omega square y square. Kinetic energy is half m omega square bracket a square minus y square. Now just expand this particular part. You will get half m omega square y square plus half m omega square a square minus half m omega square y square. This part and this part same, but in opposite sign. So they will cancel out. So you're left with half m omega square a square. This is nothing but equals to maximum kinetic energy or maximum potential energy, and it is always constant. Abhinav, any doubt?
No, sir.
Okay, just write it down. Yusuf, done?
Sir, writing total energy.
Okay.
Done, sir.
आया बड़ा बोला ना मरियम
So related to this part, we may define their relation of time period and frequency. The relation between time period and frequency for different terms. First, displacement. Next is velocity. Next, acceleration. Potential energy, kinetic energy, and total energy. For displacement, let's say time period is t and frequency f. So for velocity, it will be same, and for acceleration, it will be same. But in case of potential energy, time period will become half as that of displacement, and so frequency will become double. Similarly, in terms of kinetic energy, time period will become half and frequency will become twice. But in case of total energy, which is constant, so time period will become infinite and frequency will be zero. So this is the relation between time period and frequency related to different physical quantity in SHM. Tiba, is it clear?
Clear, sir.
Just write it down.
And sir,
Yusuf, done?
Yes, sir.
Now, there will be questions related to this part. Particle having mass 2 kg and SHM having displacement as y equals to 0.02 sine 10 pi t. So find First, time period, frequency related to this displacement, kinetic energy maximum, frequency of oscillating potential energy. Let me define you how to solve. First, for general expression of displacement, just compare y equals to a times sine omega times t. These two expressions. So you'll get a, that is coefficient of sine, which is equals to 0.02 meter. Similarly, coefficient of time is omega, which is equals to 10 pi. Now on comparing, we can write these two different quantity on the base of which you will get omega equals to 2 pi by t, that is time period, and then frequency will be equals to 1 over time period. Next, we have to calculate kinetic energy maximum, which was equals to half m omega square a square. We have mass of body 2 kg, omega and a from this expression. Put these values and you will get maximum kinetic energy. Try to solve these different terms.
Sir, can you read the question?
Particle having mass 2 kg in SHM, having displacement as this.
Thank you, sir.
Good, Atif. On comparing these two equations, you will write A equals to 0.02 meter and omega is equals to 10 pi. So 2 pi by t equals to 10 pi. So t will equals to 2 by 10, that is 0.2 second. And frequency will be 1 by 0.2. So it will be just 5 hertz. Yusuf, any doubt?
No,
Now we have to calculate kinetic energy maximum. So half mass of body, we have 2 kg. Omega is 10 pi squared and amplitude 0.02 square. So on solving, 2 and 2 will cancel out. 10 square will be 100. Pi square 0.02 square will be 2 into 10 to the power or just 4 into 4 into 10 to the power minus 4. Pi square is roughly equals to 10. So it will be 100 into 10 into 4 into 10 to the power minus 4. So this is 10 to the power 3 and this is 10 to the power minus 4. So on solving, you will get 10 to the power minus 1 multiplied by 4. So it will be 0.4 joule. Atif, is it clear?
Yes, sir.
Now, from this above table, we can say if you have time period and frequency for displacement, so potential energy must have time period half of that of displacement and frequency twice of that of displacement. So in this part, we have time period of displacement 0.2 second. So if you will be asked to find time period of kinetic energy or potential energy, it will be half of that of displacement. That is 0.1 second. Similarly, frequency will be twice of that of displacement. So we can say for displacement, we have frequency 5 hertz. So for oscillating potential energy, it will be twice of that. That will be 10 hertz. Is it clear?
Yes, sir.
So for oscillating potential energy, its frequency will be twice of that of displacement, that is 10 hertz. Abhinav, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Umar, any doubt? Yusuf, done?
yes, sir.
Okay. Next, we have to plot the graph of these different variation, that is potential energy, kinetic energy, and total energy. So next is graph of variation of these different quantity. This is energy versus displacement. So for potential energy, which is minimum at mean position, maximum at extreme position, so graph will be like this. This is potential energy or variation of potential energy with respect to displacement. Next is kinetic energy, which is maximum at mean position and minimum at extreme position. So it will be like this. And point of intersection, that is this point and this point, if you draw or join these 2 points, it will be kinetic energy equals to potential energy and half of total energy. So displacement of this particular point will be a by root 2, and this point will be minus of a by root 2. This is one extreme and this is one extreme, and this is mean position. So the blue one is for kinetic energy and this black one will be for total energy, which is constant for this entire motion. Is it clear?
Yes, sir.
Okay, just draw this particular graph. Trishan, any doubt? Yusuf, done?
Done, sir.
Okay,
Done, sir.
So this is all about the energy part of this SHM, and you'll be asked only these different problems related to this part. Next is third part of this chapter is calculation of time period. So for any problem, first try to analyze or calculate restoring force. So F restoring equals to minus of K times X, where K is called spring constant or force constant and X is displacement. So K is spring or force constant. So you may write force is equals to mass times acceleration equals to minus of kx. So acceleration is equals to minus of k by m times x. Now, as velocity is dy over dt and acceleration is d over dt of velocity. So put this v as dy over dt. So you will get d and d becomes d2y and dt and dt becomes dt square. So in place of acceleration, you may write second differentiation of displacement with respect to time plus move this quantity to left side. So you'll get k by m times x equals to 0. Now just compare this expression to the above part general expression for SHM. So you will get the coefficient of displacement in this part is k by m. And let me show you what we had derived in last class. This one, general differential equation of SHM. So for displacement or coefficient of displacement, it is omega square. So we can compare this expression with that part. Atif, is it clear?
Yes, sir.
So on comparing these two different quantity, we can say omega square equals to k by m, or simply k equals to m times omega square. That's why in terms of energy, I had written k is equals to m omega squared. Further, we have to calculate time period. So move this square to right side. So you'll get omega equals to root under k by m. Omega is nothing but 2 pi over t. So we can write time period equals to 2 pi root under m by k. So this will be our final expression for getting time period if we have force is equals to minus of kx, then time period will be equals to 2 pi root under m by k. Riba, any doubt?
No, sir.
Okay, just write it down. On this basis, I will define you different problems such as spring mass system, simple pendulum. Aisha, any doubt?
No, sir.
Okay. Yusuf, done?
Yes, sir.
Abhinav, any doubt?
No, sir.
You have to calculate first for simple pendulum. Suppose from any support, mean position is this. A bob attached with a string having length L, mass M, is slightly bent at some angle theta. So at this point, it will experience mg along this way. If you extend this particular line, this will be theta, and perpendicular to it. So there will be two different components of this particular force related to this theta. We may resolve like mg cos theta adjacent to this thing and mg sin theta opposite of it. Next, this bob will oscillate along this way. So opposite to theta, displacement from this point to this point is x. So first we have to calculate restoring force responsible to bring this bob back to its original position. Abhinav, just tell me which force will be responsible to move this bob back to its initial position, mg cos theta or mg sin theta? Riba, which force will be responsible? Since mg cos theta is acting along the string, so there will be no motion related to that part. So only left with just mg sin theta, which will tend to move this bob back to its initial position. So mg sin theta will act as a restoring force in this part. Atif, is it clear?
Yes, sir.
So restoring force will be mg times sin theta. And since it is restoring in nature, so there will be negative sign with it. Now, for a small angle, sine of theta is equals to just theta. So this equation will be minus of mg times sine theta. Now, theta equals to length of arc by radius. So we may write theta equals to x by L from this part. So put this in this expression, you will get minus of mg times theta, which is x by L, equals to restoring force. Now, in above part, I defined you, whenever you have F restoring equals to displacement times some constant attached with it, that constant behaves as spring constant, or which is called K. So we can say this particular point T or K. So from this part, we can say K equals to mg by L as related to the above expression. Riba, is it clear?
Yes, sir.
So what will be time period related to this oscillation? So time period will be equals to 2 pi root under m by k. So on putting the value of k, you will get m by k, which is mg divided by L. M and M cancel out, so you'll get 2 pi root under L by G. So this is your final time period for simple pendulum or oscillating bob. Aisha, any doubt?
No, sir.
Just write it down.
Done, sir.
Yusuf, done?
So drawing the diagram.
Okay.
Done, sir.
Now related to this expression, you will be asked, as time period of simple pendulum is 2 pi root under L by G. So this L is called distance of center of mass from axis of rotation. And this G is called net acceleration. So first question will be, what will be the time period of simple pendulum if it is placed at the center of Earth? So first, what will be the acceleration of gravity at center of Earth? Atif, any idea about it?
Sorry, sir.
What will be the value of gravity at center of Earth?
Not sure.
0. Okay. So if you put the value of G to be 0 in this above part, what you will get for time period? 0 or something else? Abhinav?
Anything by 0 is not defined, right?
Not defined is also called infinity. Now you are in class 11.
Yes.
So it must be infinite. So time period in this case will be infinite. Similarly, in free falling or free fall, net acceleration will be 0. So again, time period will be infinite. So this time period of simple pendulum may depend upon these two factors like this, and you'll be given system and surrounding on the basis of which you may define its net acceleration and then time period. Suppose you'll be asked what will happen to the time period of simple pendulum when it is placed on the surface of moon. So you'll say gravity on the surface of moon will be smaller as compared to Earth. So if gravity decreases or acceleration decreases, time period must increases. Hence, time period of pendulum increases as compared to Earth. Atif, is it clear?
Yes, sir.
Okay, just write it down. Next is spring mass system. Suppose you have spring and a block it is attached to it. This is mean position, spring constant K. So if you displace this particular spring to any one side, the restoring force will be just minus of Kx. So time period related to this part will be 2 pi root under m by k. So first, we have to define how will spring constant be affected with respect to length. Suppose you have spring having area of cross section A, length L. So K equals to YA divided by L, where Y is elasticity or simply Young's modulus, A is area of cross section, and L is length of this spring, natural length of spring. So you'll be asked, what will happen if you cut this particular spring in some segment? Suppose this is string and I've cut it into some segment. First, this, in which this is one part, this is two part, and this is three part. So you'll be asked, how will spring constant of these three different segments related with actual spring constant K? Since these three different segments are in ratio, so you can say first segment is X part, second segment is 2X part, and third segment is 3X part. Sum of all these three different lengths will be equals to natural length L of this particular spring. Now on adding x plus 2x plus 3x, 6x equals to L, or x is equals to L by 6. Now for each different part, first part having length L, which is equals to second part having length 2x, so it should be equals to, and third part having length 3x, so it will be equals to. Now we can say K1 equals to YA divided by its length, that is L by 6. K2 is equals to YA divided by its length, L by 3. And K3 equals to YA divided by L, that is L by 2. Now just compare this part to the above one, as K equals to YA by L. So if you put this in this part, in this one, and in this one, so K1 equals to 6 times of K, K2 equals to 3 times of K, and K3 equals to 2 times of K. So this is how we can calculate the spring constant on dividing it in different segments. Atif, is it clear?
Yes.
Okay, just write it down. Aisha, any doubt?
No, sir.
Abhinav, done?
1 minute, sir.
Done, sir.
Done, sir.
Yusuf, done?
Yes, sir. Done.
Okay. Now, next we have to calculate combination of spring mass system, that is series combination and parallel combination. So next is combination of spring. First is series combination. Suppose one of the string is this, connected to another string this, and a block. Spring constant of this is K1, this is K2. Length of first spring or natural length of first spring is L1 and second spring is L2. Now on stretching it, it may extend to this point. And similarly, it will be reached at this point. So first string initially having length L1. Now, suppose X1 displacement in it, and second part X2. So total displacement from initial position to final position will be X1 plus X2, since L1 and L2 are their natural length. So in this part, we can say displacement of each spring is different. Since spring is massless, so for massless wire, string rho, tension at each point will be same. Similarly, force or restoring force for each spring will be same. So we can say force is same. This is property of series combination. So from this part, we can say net displacement equals to x1 plus x2. Now, according to the formula, F equals to K times of X. So X equals to F by K. So for equivalent part, it will be this. For X1, it will be F by K. And for X2, it will be F by K2. As for a spring mass, F equals to K times of X. So X will be equals to F by K with negative sign. I'm using this in this part. So minus F taken out common from either side. So on solving, you will get K equivalent equals to 1 by K1 and 1 by K2. Final result. Is it clear?
Yes, sir.
Riba, any doubt?
No, sir.
Okay, just write it down.
So can you scroll up for a few moments?
This part,
Yes, sir. Thank you, sir.
Have you all done?
So drawing the
Yes, sir.
diagram.
Related to this concept, try to find if you have two spring, this one and this one, having spring constant 3K and 6K and a block of mass M. So this above formula will be valid as for horizontal combination as well as for vertical combination. It will be valid for both. So this combination is series. So just use the above formula, try to find K equivalent and then time period. Try to solve. Good, Atif. Try to find next part. Good, Yusuf. Aisha, got any answer? Since combination is series, so according to the formula, we may write 1 by K equivalent equals to 1 by K1, which is 3K, and 1 by K2, which is 6K. Now take LCM as 6K. So it will be 2 plus 1, 3 by 6K. That will be 1 by 2K. So on converting into numerator, K equivalent will become 2K. Now for time period, T equals to 2 pi root under M by K, and K we have in this combination 2K, so it will be like this. Abhinav, is it clear?
Yes, sir.
Rehab, any doubt? Next is parallel combination. Suppose we have first spring and second spring attached to a block, mean position this. Spring constant K1 and a spring constant K2. Now, if it is stressed, net displacement is X. Since in this part, displacement of each spring is same, but due to different spring constant or different stiffness or flexibility, there will be different restoring force and different spring. So force will be different in this case. The next combination related to parallel will be like this. Suppose you have a spring and a block at this point. Another spring, K1 and K2. Now, if you compress any one of them, it means X amount of compression will be in black one, and similarly, X amount of extension in the red one. It means displacement for both these two springs in this part is also same. So we can say this is also parallel combination or a type of parallel combination. Atif, is it clear?
Yes.
Now, since force is different, so we can write net force equals to F1 plus F2. As F equals to minus of Kx, so it will be minus K equivalent times X minus K1 times X minus K2 times X. X cancel out. So you'll get K equivalent equals to K1 plus K2. So this will be your K equivalent for parallel combination. Riba, any doubt?
No, sir.
Just write it down.
Sir, can you scroll up?
Furthermore,
No, sir, I just wanted the diagram, sir. You can scroll down.
Yusuf, done?
1 minute, sir. Sir, where is F in the diagram?
Net force we have to define according to these two different springs. In first part, just 1 minute. When you stretch this particular spring slightly right side, a restoring force develop into it along this way. In first part, it will be F1, and the second one, it will be F2. So total force acting on this particular block will be sum of F1 and F2. Similarly, in the right side, since black spring get compressed, so restoring force will develop along this way. And this red one gets stretched, so restoring force will be again in this direction. So net force will be sum of these two forces.
Okay, sir.
Yusuf? Okay.
Done, sir.
Again, find K equivalent and time period for a combination. Okay, Umar. Let's say this is K, this is 2K, and this is 3K. So find K equivalent for this particular part and then time period. First, try to analyze which of these this part is in series and parallel. Then apply the formula according to it. First, check this combination about this spring and this spring. Is it in series or parallel? Atif,
In parallel.
good. So if you combine these two springs together, you'll get K equivalent for this part. So your system will now become like this. So in parallel, K equivalent equals to K1 plus K2. K1 we have K and K2 we have 3K. So on combining, it will become 3K and we have 3K in this part. Now tell me about the type of combination this is. Is it series or parallel?
Series.
Is it series? Just compare with this part. Is it series or parallel? If you have same displacement and different force, then it will be always parallel. Similarly, in this part, if you compress or elongate towards any one side in both spring, it will have same displacement. So it is again in parallel combination. Atif, is it clear?
Yes, sir.
So K equivalent now will be K1, K2. So it will be 6K. And time period equals to 2 pi root under M by K. In this part, we have 6K. Abhinav, any doubt?
No doubt, sir.
Good. Yusuf, any doubt?
No, sir.
Yusuf, done up to this part?
Yes, sir. Done.
Next is, this is all about series or parallel combination of the spring mass system. Next, we may define this oscillation into two categories. One is called undamped oscillation, and the other is damped oscillation. Suppose a spring mass system and the other one in first part, if there is no viscous medium around it, so it will oscillate like this. But in second part, suppose there is some viscous medium. like any liquid. So due to this viscous medium, or other than vacuum or air, a force will act on this ball due to viscosity of this particular medium, which is called viscous force. So in first part, net force acting on this spring mass system will be F equals to minus of K into Y. So force will be equals to mass times acceleration, K times Y, or acceleration equals to minus of K by M times Y. We may write acceleration as second differentiation of displacement plus K by M times Y equals to 0. So this will be general expression for this part. If you solve this, you will get Y equals to sum A times sine omega t. So in this part, amplitude of oscillating bob will be constant. So if there is no change in amplitude of oscillation, that is called undamped oscillation. So if you plot the variation of displacement versus time for this part, y versus t. It will be like this. It means if there is no change in amplitude, that will be called undamped oscillation. But in second part, due to its motion, a viscous force or drag force will also act on this part. So net force in this case will be minus of B times V. I defined this particular term in viscosity about in Stokes' law. And next is spring force. So you may write force equals to mass times acceleration minus of B times V ky. Acceleration equals to minus B by M into velocity and K by M into displacement. So you may write acceleration as double derivative of displacement plus B by M. Velocity is dy over dt plus K by M times equals to 0. So this will be general expression in this part. If you simplify it, you'll get your answer as y equals to sum a naught e to the power cos omega dash t plus phi. We have to define only this part, amplitude part. So in this, we can say amplitude is continuously decreasing as exponential rate. A is equals to a naught e to the power b by 2m into t. So it means in an oscillation, if amplitude of particle exponential decreases due to viscous force or drag force of its surrounding medium, that is called damped oscillation. So if you plot the variation of amplitude for this part, it will be like this. Abhinav, Is it clear?
Clear, sir.
So you'll be asked only to define these two words and nothing more. Just write it down to this part. Have you all done?
Yes, sir.
Yes, sir.
Yusuf, done?
Diagram, sir.
Okay. So this is all about oscillation, entire chapter. So let's stop here for today. In next class, I'll define you some term related to this part, and then we'll start new chapter, waves. Okay. Okay then, take care. Thank you.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you.
Done, sir.